So here's a quick exam tip. Right at the start of the exam, you should try and scan through the whole paper and see if you can find different units of measurements. For example, in this question here, you have meters here and you have millimeters here. So when you see something like that, you should underline them. Because if you notice, the answer has to be in meter cubed, so you're going to have to change this millimeter into meters. And sometimes, if you leave this till later in the exam, you may be a bit tired. You might not notice that they're using different units of measurements here. So that's just a tip. Scan through. You don't have to do the question, just underline the different units of measurements so that you'll notice them when you're actually doing the question. Now, I think area and volume is one of the easiest questions to pick up marks in the exam. I know a lot of people get intimidated by area and volume because they sometimes look a bit complicated, but the important thing you need to know really is that all of these questions just deal with various types of shapes, and if you can identify the shapes and then write down the correct formulas, which is just a case of looking up the formula in the log tables mostly. If you write the correct formula out and put in the correct amounts into the variables, and you just do this part alone, you've already got an honor in that question basically. So you really just need to look up the formulas in the log tables and put in the correct amounts into the variables. Now some questions, right, they might say, for example, this question here, it's looking for the volume of this cylinder. So you're going to use the formula, you're going to plug in the amounts, and then they might say something in the question like, give your answer in terms of pi. So in that case, you wouldn't multiply the pi by this, these amounts here. You would simply leave your answer as 500 pi. On the other hand, sometimes you might be asked to give your answer to a certain amount of decimal places. In that case, you would multiply the 500 by the pi. And finally, don't forget to put in the cm cubed, because you actually get marked for putting in the unit of measurement. Here we're dealing with centimeters, so as it's volume we're talking about, it's going to be cm cubed. Volume is always cubed and area is always squared. To be really successful with area and volume questions, you need to read the question a few times. Take this question here, for example. It says, the diagram shows two pulley wheels of equal size connected by a drive belt. The radius of each wheel is 7 centimeters and the distance between the centers is 28 centimeters. Calculate the length of the belt, give your answer correct to the nearest whole number. I know a lot of people get confused by this because pulley wheels and drive belts is not something most people are familiar with, and so that might put you off when you first read it. But the key is to read it maybe a second time or a third time and you get it, because you can actually work this out. Well, pulley wheels, the only things that could be wheels here are obviously these two guys. Now the confusing part for most people is the belt. It says the belt connects the two wheels, so most people seem to think that it's this line here. But if you think about what a belt is, it's something that goes around your waist. So actually the drive belt is something that's going around the wheels, the pulley wheels. And the wheels are pulling the belt around. And also, it wouldn't make much sense for the belt to be this section here, because we're already given the length of this. So why would they ask to calculate the length of the belt if they already give us the length of the belt? So clearly the belt is the thing, like a bicycle chain. It's going around the wheels here, and this is what we need to get the length of. So reading the question is very important. Reading it a few times on, you absolutely sure you know what the meaning of the question is, because if you realize what this actually represents, then you can get the correct formulas for this problem, and once you have the correct formulas, you get most of the marks. So a common mistake here for people is just to look at the diagram alone and think that maybe that looks like a cylinder, because it kind of does look like a cylinder if you turn it into a three-dimensional shape. But you can clearly rule out that if you just read this question long enough. You see that there's no way it can be a cylinder. A big mistake there would have been to write the formula for a cylinder, because there's no cylinder involved here. So you want to get the correct shapes. And also, most questions involve a mixture of shapes. So what you want to do is you want to divide this single shape here into a bunch of shapes that you can work with. This shape itself you can't find in the log tables, but you can find, for example, a semicircle like this, and you can find a semicircle like this. And if you realize that from here to here is 28 centimeters, and here to here is 28 centimeters also, then you just add them all up, these two 28s, and get the lengths of each semicircle. Another way of thinking about that is if you join the semicircles together, you get a circle. So all you need to do is get the length of a circle with a radius of 7 centimeters to be able to get the length of this part and the length of this part, and then you simply add it to the two lengths here to get the total length of the belt. So in my heading I say read carefully and make deductions. The make deductions part refers to, if you get a diagram like this, for example, you want to put any deductions that you can make onto the diagram. So because we know this is 28, we can deduce that this from here to here must be 28 also, and from here to here must be 28. So as I said, to get the total length, we just add the two 28s to give us 56, and we kind of join the two semicircles together into a circle, which will have the length formula 2 pi r, and the radius would be, of course, be 7, so 2 pi times 7 gives you 14 pi, and then you simply key that into your calculator and you get the length of the belt. So when it comes to three-dimensional objects like these here, there's only ever two formulas that you're concerned with. One is the volume and the other is the surface area. Now, volume refers to the space that the object takes up. Think of it as the content of the object, but the surface area is just the outside of the object, the part that you can just see and touch. Now, it's important too to understand what the formulas regarding surface area refer to in the log tables. They only refer to the curved surface area. So the curved surface area is, for example, in the cylinder, is just the side of the cylinder, the part that is curved. It doesn't refer to the bottom of the cylinder, which is flat, nor does it refer to the top of the cylinder. Likewise with the cone, it's just the curved part of the cone. So it doesn't refer to the circular base. Now in the exam, you've got to watch out for the language that they use, these questions, because if they just say curved surface area, then you have no problem. You just use the formula that you get in your log tables. But if they say total surface area, for example, find the total surface area of this cylinder, what you're going to have to do is you're going to have to add the area of the base and the top to the curved surface area that you find in your log tables. 2 pi RH is the formula you get from your log tables for the curved surface area, and then each of the flat circles will be, of course, be pi r squared, have an area of pi r squared. So the total surface area will be 2 times pi r squared, so 2 pi r squared plus 2 pi RH, plus 2 pi RH. Similarly, if we look at the cone here, we have to divide that up into the curved surface area, which is pi r L. This is what you get in your log tables. And of course the flat base here, again it's a circle, so that's pi r squared. So the total surface area of a cone would be pi r L plus pi r squared. Finally, this cylinder object here is from an exam question that many students find particularly difficult. So describe this object. It's a solid object, except for kind of a hemisphere shape has been excavated from the top of the object. So the question is, first of all, how do you find the curved surface area? Well, that's just the curved surface area of a cylinder, so it'll be 2 pi RH. But if you want to find the total surface area, then you're going to have to add the 2 pi RH to the pi r squared for the base of the cylinder, and then you're going to have to find out what is the surface area of this kind of excavated shape here. Now, in this particular question, it was said that a part of the solid cylinder was removed that was in the shape of a hemisphere. So this is like an excavated part of the object, Because of this, many students think that you have to subtract the surface area of a hemisphere to get the total surface area of the object. But that's not really understanding it properly, because if you remove this hemisphere shape from the object, you're still leaving behind an imprint. Something, you're not leaving behind fresh air, you're leaving something there that you can touch, and that's a surface as well. So if that's an additional surface area, then we have to add that to the 2 pi r h and to the pi r squared. Now if you look up your log tables, you're not going to find the formula for the surface area of a hemisphere. You can only find the surface area of a sphere. And as a hemisphere is half of a sphere, all we have to do is divide this by 2 to get the surface area of a hemisphere. So now we all have all that we need to get our total surface area. We add these 3 formulas here. Finally, I briefly mentioned this solid hemisphere here. How would you get the total surface area of that? Well, you might think it's just dividing this by 2 as we did here, but remember this is a solid hemisphere, so we're not only talking about the curved surface area, we're also talking about this flat circle here. And as that's pi r squared, we just add that to 2 pi r squared to get 3 pi r squared. So if you're getting the total surface area of a hemisphere, a solid hemisphere, then you need to include the top as well, just like we had to include the base here and the base here. So on this page I've given you examples taken from exam questions over the years. So these are all mixed shapes, I call them. Now, as I said before, to get most of the marks in an area volume question, all you have to do is correctly recognize what all the shapes are. So for example, in this shape here, it comprises of 2 spheres, 2 cubes, and then a rectangular block or a cuboid. So as this question only relates to volume, all you need to do is get the volume formula for a cube, a sphere, and a cuboid. And once you have those 3 formulas, then you can plug in the measurements, and you've already got your honour in that question. Now, it's important to note though that the formula for a cuboid is not given in the log tables. So what I'll do at the end of this video is tell you all of the formulas that you're expected to know and that you won't be able to find in the log tables. So if you look at this second image here, again this is a cylinder, and it also has a hemisphere cut out of it, hemisphere shape cut out of it. So the question here was actually to do with surface area, and we talked a little bit about that in the previous section. To get the surface area, you need to just identify the 3 main parts of this object: the bottom, the base, the flat circle base, the curved surface area here, and the surface area of the top here, which is in the shape of a hemisphere. So this question here is also a pretty straightforward question. The question was to get the volume of the object. Now, as you can see, it's made up of a cylinder and a hemisphere. So that's what we have to do in our heads, divide it up into 2 different shapes, and then get the volume formulas for each shape. Pretty easy. Now the only tricky bit about this is what do you take as the height of the cylinder? And this 20 centimeters here, after all, is the height of the whole object, not the height of the cylinder part. So we need to figure out what is the height of the hemisphere.
And the key here is to realize that the radius of the hemisphere is also equal to the height of the hemisphere. Remember, radius really means from the center of the sphere or the hemisphere to the edges of the hemisphere. So radius can go in any direction. So here is what we normally think of as the radius, but the radius can go in this direction, and this direction. So that would give you then the height of the hemisphere. So in this case, of course, the radius will be 6 centimeters. So that would mean that the height of the hemisphere is 6 centimeters. That would mean the height of the cylinder must be 14 centimeters. In other words, take 6 from 20. So once we have all that information, we simply use the two formulas for the two shapes and add them together to get the total volume of the object. Now if we look at this object here, it's kind of a similar type of question to the one we've just done. The question is find the volume of this float shape which is within a cylinder. So you just have to find the volume of the float which is in the shape of a cone on top of a hemisphere. So again you find the volume of the cone and the volume of the hemisphere, and again you have this problem figuring out the height of the cone. The whole thing is 60, so you have to subtract the radius of the hemisphere, which would be half of 30. So subtract 15 from 60 to get the height of the cone, which would be 45. Once you have those details, then you can plug them into the two formulas, add them together, and you've solved that problem. Now in this problem here, the first part of the question asks us to find the area of this section here, CDE, so kind of a slice shape, and also the area of this circle here. So let's just assume we know both the answers for these two areas. The next question is find the total area of the two together. So you might think that's just adding the two of them together, but remember this part here, this section here, belongs to both shapes, so we have to take that out somehow. And the way we do that is pretty simple. We realize that this here is a 90-degree angle, so that means this sector here is a quarter of the whole circle, because a whole circle is 360 degrees, that's 90 degrees. 90 degrees is a quarter of 360. So we can work out, we could do it a number of ways, but I would say the easiest way to do it is get 3/4 of the circle to represent that part of the circle, and add it to the area of this sector here, sector C, D, and E.
Now, another very common question you get in area and volume is, for example, you're asked about an object that's been carved out of a solid object, and you might be asked what was the part of the object that was carved away, or what percentage of the object was carved away. So this is a typical example here. You've got an ornament that's made up of cubes and spheres that was carved out of a solid rectangular block. And I think the question was, what percentage of the block was carved away? So what we need to do is find, first of all, what the volume of the carved away part is, and then get that as a percentage of the total block. So to solve this, we need to get, first of all, what we've already done before. We got the volume of the ornament, and then we have to get the volume of the block itself and subtract to get the volume of the carved away part. Now the volume formula for a block would be the length by the width by the height. That's another formula that you're not going to find in your log tables, so you need to remember this. So in this second problem here, pretty similar situation. You've got a solid cylinder and a cone is excavated from it, and the question was how much was left after the cone was removed from the cylinder. So again, you could do it like we did the previous question. You could find the volume of the cylinder and take away the volume of the cone. That will give you the volume of the remaining cylinder, and then make that into a percentage of the total volume of the cylinder. Or you could be even cleverer about this, because if you look at the formulas for volume of a cylinder is pi r squared h, and the volume of a cone is a third pi r squared h. So really a cone is a third of a cylinder if they have the same dimensions. So that means if you take out a third of the cylinder, you're left with 2/3 remaining. And finally, this question here, pretty similar question, a solid cylinder, and you've got a float that's made up of a cone and a hemisphere. And I think the question was, like the other ones, how much was remaining after the float was removed. Again, you do the same thing. You get the volume of all of this, get volume of the whole cylinder, and then take the volume of this from the volume of the cylinder. So this is the end of part one. There's actually a second part to this because I couldn't possibly fit area and volume into one video. So look that up on YouTube. If you're interested in more videos of this kind, that summarize difficult topics on a junior cert, you can check out my website www.danswers.ie.